And simply we will discuss the mathematical modeling of physical system. So we'll discuss the mathematical modeling of physical systems. So I think last time we agreed that we will have a system. If we have a system, now this system has an input and output. It can be single input, single output. It can be multi-input, multi-output. So this is an input, and here we have output. Now this is a physical system. Which means that this is a real system. Huh? So simply this can be, let's say, it can be car. It can be, let's say, oven. It can be ship. It can be, let's say, airplane. It can be washing machine. It can be motor, and so on. So it's a physical system, huh? Some hardware. Let's say a system which consists of a lot of elements that behave together in order to achieve certain functions. For example, for the car, the mobility. For the oven, to cook the food, let's say. Now, in general, the first thing, if we need to mathematical model of the physical system, so the first thing here, we should understand the physical system itself. So simply, we need to understand the physical system. Which mean what? We need to understand the physics behind the system. So we need to understand the physics. And also we need to specify the input and the output. So we need to determine or understand the input and the output. Who can answer me why it's very important to specify the input and the output for the system, for the physical system? Let me choose. Ahmed, Muhammad, this one. Muhammad. Okay. Why it's very important to understand or determine the input and the output of the physical system?
عشان نحدد الطريقة اللي بدنا نحول الانبوت لاوتبوت.
So I will rephrase it. In order to control the output, I must understand what quantity I need to change. Yes? For example, if I need to control the speed of the motor, I must understand that in order to control the speed of the motor, I need to control the voltage. For example, huh? Yes? Later on, you say, no. If I need to control the speed of the motor, I must control the torque of the motor. And so I need to control the current of the motor. So I need to control the voltage of the motor. So it's like cascade control now. You have a voltage control, then you will have a current control, which actually a torque control. So this is very important. The first thing you must understand what's the output and what's the input you have. Because simply if you have a system and you cannot adjust the output, this will be uncontrollable system or a system you cannot control. So the first thing, we must understand the physics, how the system is working, what quantity, if I change, then what quantity will be changed according to that, and this is actually the input and the output. And in general, the output is what? Something we are interested in, yes? Yes or no? The output is something we are interested in to achieve a desired performance. Yep. So this is the first thing in the modeling. I must understand the physics and I must determine the input and the output. Then I must represent the physical system in mathematics. So I must represent the physical system. This is the which mean what? Which means that I will assume that I'm having the same system, but virtually written as a set of equations. And this system has the same input. And I'm hoping that I will achieve the same output. And this will be the mathematical model. So the math model is actually a set of equations. A set of mathematical equations in general that represents the dynamic of the system of the physical system let's say accurately or very well. Or at least, let's say, fairly well. So this is a math, actually. Huh? This is a math. So in general, if I need to distinguish between the two systems or if I need to compare, let's give this one y physics of t, the output here, and let's give this one y math of t. So the ideal case, let's say the ideal case, is to have the two outputs are identical, which means that y math of t is equal y physics of t. Is it possible, this one? Is this one possible to achieve an accurate modeling? This called actually exact modeling. Is it possible? Let's ask.
لا دكتور مش ممكن.
Why?
دائما بكون في عنا شو بسموه يعني إشي ما بخليش المعادلة تكمل، ظرف استثنائي، معادلات مش موجودة يعني بس on real life يعني ما بزبط دائما الفيزيكس ثيوري.
Let's see this is a simple example. Huh?
تمام.
This is actually a voltage and resistance.
في زي تشويش زي يعني في ايرور، هذا الايرور حيختلف بين الماث والفيزيكس. يعني المقاومه ايديالي مثلا تكون 1000 اوم، بس لما نقيسها بيكون مثلا 990 او شيء زي هيك. هذا الاختلاف بين الفيزيكس والماث.
Very good. So simply this means that there's a mismatch, whatever this mismatch is, due to the measurement error, due to the aging, due to a disturbance, due to let's say tolerance and so on. Yes. Now, do you see this circuit? Very simple circuit, huh? Now, if I need to find the current, I is equal according to Ohm law what? V over R, correct? Yes.
Yes.
Yes. So simply this means that the current is proportional with the voltage. Yes or no?
Yes.
Yeah, assuming that this one is what is constant. Yep. Yes.
طيب.
Okay.
Yes.
Now you know that if there's a current in the conductor, then a heat will generate it according to I square R, correct? A power will generate it, and this actually is the heat. Yeah.
صحيح دكتور.
So if I'm heating the resistance, this means that the resistance can be nonlinear at certain sense. Yes.
صحيح.
So similarly, this means that also, if I'm assuming that this one is 10 ohm, yeah, this is what I'm assuming in my model, but in practice, if I go to the lab and measure the resistance, it will be 10 plus minus the tolerance, let's say 10%. Huh? Yes, this is another thing. Another thing also, if I need to capture the physics 100%, I need, let's say, huge set of mathematical model. Maybe I need 1 trillion mathematical equation in order to capture the physics, and I will not. I could not, I will not, or I could not capture the physics. So in the end of the day, this one is impossible. Huh? This one is what? Is impossible. So the best that we can have is what? That for the model to be what? Fairly well, huh? To capture the main feature of the system, which means that the difference between y math of t minus y physics of t as absolute value is less than or equal certain constant, and this one is a small positive number, epsilon, let's say, yeah? Small positive number. Now this one can be 1%, 2%, 3%, less than that or greater than that, according to what? To the application. According to what? To the application. So simply now, while doing the modeling, we have two things to think about. The first one is what? The first one is the complexity of the model, and the second one is what? The accuracy of the model, correct? Yes. So simply, while, let's say, modeling the physical system, a trade-off between the accuracy of the model, or let's say the simplicity of the model, and the accuracy of the response. So between the simplicity of the model and the accuracy, let's say, of the system, of the analysis. Yes. So simply, let's assume that I'm having this example. And let's assume this is the displacement X, and this is the force due to the engine. Now I need to model this system, for example. How I can model it? Now we know that this is a mechanical system. If I'm looking only in to the mobility, so I can use a Newton's second law, which said that the summation of the force must equal to what? The mass multiplied by the acceleration. And we know that here we have friction, let's say Fr. Then we say that F engine minus Fr will equal the mass multiplied by the acceleration. We know that the acceleration is the second derivative of what? Of the displacement, correct? So this will be d square x by dt square. Yeah?
I didn't understand that.
So correct? Now, this model actually is very simple, yeah? This model actually is very simple, but can it capture the main feature of the physical system?
No.
No. So simply we need to add more modeling, huh? We need to consider, let's say, more interaction between the wheel, the engine, and so on. Huh? So in the end of the day, you must do a trade-off. You must do a compromise between the simplicity of the model and the accuracy of the result. Now, what's the meaning of the accuracy of the result? This means that the mathematical model can capture the main feature of the physical system. So the accuracy, or at least we need a model, a mathematical model, to capture the main feature of the physical system. Which means what? If the physical system is unstable, then the mathematical system is unstable, or the mathematical system can judge about the stability of the physical system. So the main features such as stability, such as controllability, or observability. The first one, it means what? If I'm having a set of equations and this equation tell me that the system is unstable, then that is unstable. If this set of equations tell me that the math is stable, then the physical system will be stable. But not the math tell me that the system is stable while the physical system is unstable. Here, it will be a very serious problem. The second one is the controllability, which means that the math should give me indication. Can I control the system or no? So simply, if I'm having a set of math, the math tell me that I can't control the physics, but when I go to the physics, I will discover that I cannot control. This is a very serious problem. So simply, the math must give me also, can I control the system, yes or no? The last one is the observability, let's say. The same thing. The math can't tell me from the knowledge of the input and the output, can I estimate the state? Can I know all the internal dynamic of the system? This is also one of the key features of the mathematical model. So someone will say, why I need in the first stage mathematical model? I have the car, for example. Huh? I have the car. So I can control it or I can analyze it, huh? Because in the end of the day, I need a mathematical model in order to analyze the system. And after that, I need the mathematical model in order to control the system. So someone will say, I have the car. So if I'm having the car, I will design my control and I will drive it here and I will test all of my new, let's say, driving technique on the car without the need of the mathematical model. Is it valid?
No.
Why? Raha?
Raha, yes.
Why? Why is not valid?
Because ممكن يكون في side effects كبار أو الضرر يكون أكبر لو ما جربت mathematically أول.
So simply, someone will say, yeah, I will rephrase it. Someone will say, if you are testing the physical system, maybe the physical system will be damaged, correct? So now, in order to retest again, you need another physical system, and this will be very expensive, yes or no?
Yes.
The second thing, maybe sometime you don't have the chance to do it again because you are putting your life and the other lives in danger. So simply in the first stage, we need to test or analyze the system using what? Using the mathematical model. Using what? The mathematical model. That's why we need the modeling. And the modeling is what? Is a set of equations. So if this equation go to infinity or if this equation collapse, I don't care. It's actually in the end of the day equation. I can resimulate my equation. I can remodify it until I'm getting satisfactory, let's say, performance. Then after that, I will design a controller for this mathematical system to achieve, let's say, desired performance. Yes. Then I will implement my control to the physical system. But at least now, I'm having a knowledge. I'm having, let's say, a start point in order to start with the physical system, while I know that my system is stable. I know my system will behave almost as intended, but at least I need to do some fine tuning because of the mismatch between, let's say, the mathematical model and the physics. Yes? Yep. Okay. Now, mathematical model, mathematical set of equations. This means that the model or the math, the mathematical model, can be what? Can be differential equation, correct? Can be what? Algebraical equation? Can be what?
Laplace equation.
Can be what? Differential integral equation? Can be what? Can be
Laplace.
No, Laplace is a tool, not actually the physical system in time domain. This is something you should understand, that any physical system is a time domain system. Now, Laplace is a tool in order to simplify our solution for the time domain system. But simply, this is what we can have. We can have differential equation. We can have algebraical equation. We can have partial differential equation. We can have differential integral equation. Actually, differential integral equation is actually a differential equation. Why? Because I can differentiate all the equation, and I will end up with what? With a differential equation. Now, in this course, we are interested in something called linear time invariant system. So in this course, we are interested in linear time invariant system. Now, the first thing, what's the meaning of the linear?
خطي.
خطي. So this is let's say transition. What's the meaning? خطي. So خطي is what? خطي is what? Linear time invariant system.
انه معادله بيكون الاسس فيها بتساوي واحد.
Okay. So according to your definition, xy plus 1 dx by dt, dy by dt equal y plus 1. This one is linear.
دكتور لينير يعني اي شيء بغيره للانبوت بتغير نفس الشيء للاوتبوت.
Which we call it the superposition principle, huh? Yeah, any system obeys the superposition principle is called linear. And simply, I think you know the superposition principle, correct? If I'm having a system here, and for this system, I'm having input and output, and I'm injected here certain input, let's assume U1, and I'm achieving Y1, and this is for the system. Then for the same system, if I'm injecting another input, let's say U2, I will achieve Y2 for the same system. Huh? Now, the superposition principle states that if I'm having K1, U1 plus K2, U2 as the input, and I inject it to the same system, then I will get Y, which actually a combination of K1, Y1 plus K2, Y2, such that K1 and K2 must be constant, huh? Such that K1 and K2 are constant. This is actually called what? The superposition principle. Huh? This one is called the superposition principle. I think you know it, the superposition principle. Use it. Use it where? In the circuit, huh? In the circuit analysis. Let's assume here I'm having, let's say, a simple circuit. Here 2 ohm, here 2 ohm, and here I'm having a supply voltage. Let's assume it will be 3 to make it easy for the calculation. And here I'm having another 2 ohm, and here I'm having a current source. Huh? And this current source is, let's assume 1 ampere. And I need to find the current here. You did the superposition, correct? Yes or no?
Sorry, Doctor.
No. So in the superposition, what you have, you state what? You state in the first thing you are killing one of the sources, correct? Do you see? I'm having here 2 excitation, by the way. Huh? This is actually an excitation. U1 and U2 is external signal, huh? And here the voltage 3 volt, the supply, and 1 ampere, the current supply, is also external signal, correct? Injected to what? To the system. Let's assume this is my system. Huh? Yes? Yeah. So simply, if I need to kill, which one you need to kill? The 3 volt, I will put short circuit instead of that, yeah? So this will be 1 ohm, yeah? And the current will be 1 ampere divided by the 1 and the 1. So this will be what? This will be 0.5 due to this current, yes? So I1 is equal 0.5 ampere. And I2, due to the 3 volt here, I will kill the current source, and killing the current source, I will put what? Open circuit instead of that. Huh? So the current here will be what? 3/4. So I total will equal to what? You see the summation, huh? The summation, which is 0.5, 2/4 plus 3/4, and this will be 5/4 ampere. This system is what? Is a linear system, yeah? So how to distinguish between the linear system and the non-linear system?
دكتور بتكون الزيادة ثابتة، يعني مثلا يكون لنا واي تساوي مثلا اكس، إذا زدنا 1 اكس هيزيد 1 واي، بس إذا كان واي تساوي 2 اكس كل ما زدنا 1 اكس هيزيد 2 واي.
No, actually y equal to x is a linear system.
هو بحكي linear إنه الزيادة ثابتة.
Okay. Which means the superposition is fulfilled, yes or no?
Sorry.
Okay. But according to your comment, let's highlight this one. Another example. Do you know this one what?
amplifier هون.
Yeah, the amplifier. Yep. And simply here I will have Vn, and here I will have V out. And let's assume this, you call it Rn, huh? In general, we call it Rn or R1. What you choose, Rn or R1? R1 or Rn. Let's say Rn. And this one R feedback, RF. Huh? Yes. I need to model this system. Can you know how we model the amplifier? This is actually very important, because if you need to model a physical system, you must understand the physics. Yes, you must specify the input and the output. And here the input and the output is very simple. I need, this is my input and this is my output. Yeah, and I need to model this system.
دكتور بنعمل له موديل بين الريشيو بين RF و RN.
Yeah, but do you know how that was achieved?
دكتور أول اسم
This is what we call it
ولا لا.
Z impedance, Zn, and this in theory go to infinity. Okay, which means that this is a node, and now I can calculate a current here and a current here. So I will say that the current here is Vn over Rn must equal, according to KCL, V out over RF, and all the current are in the node. So simply this means that those must be okay, plus Vn over Rn plus V out over R out must equal to 0. We don't have another current. So simply this means that V out over RF is equal minus Vn over Rn. So now I will have the famous relation, you know, which is V out is equal to what? Minus Rf over Rn multiplied by Vn. I think all of you know this relation, yes? Yeah, no. Correct? Yes. So let's assume that for simplicity, let R feedback equal to 1 kilo ohm and Rn equal to 1 ohm and Vn equal to 1 volt. Who can calculate V out equal to what?
1000 volt.
1000 volt, yeah? Yes, but this is in physics is impossible, correct? Do you know why? Because this amplifier is not passive amplifier. It needs excitation. It needs VCC and minus VCC, which means that the output now is restricted between what? Is restricted between minus VCC and VCC. So whatever I'm having again, whatever I'm having the gain, if I'm plotting here, and this is the Vn, this is the V out, the ratio between them is constant until I'm reaching VCC here and minus VCC here. So the same thing here. If the input is positive, I will get negative output until VCC, then this will be saturated. So this is actually one example of the nonlinearity, which is the saturation. So this is what we call it what? Saturation. So do you see, this system is linear to certain sense, huh? To certain sense, the system is linear. After that, the system become what? Non-linear. The system become what? Non-linear. Why? Because if I'm having input, let's say here, and I'm having input here, so this input has this output, correct? And this input has this output, let's say here. Huh? Now, if I add those two inputs, I will get somewhere here, let's say. Huh? Then I will get what? A fixed output, which is not equal to the y1 plus y2. So simply this is a system which does not obey the superposition principle, so the system become nonlinear. Good. Okay. Now, another example of the nonlinearity in the system. Who can give me another example of the nonlinear system?
دكتور مش المقاومة نفسها تظلها لينير لحد معين تصير في نون لينير أو لعند
Yeah, this is actually extreme case when you let's say when the temperature rises very high. Yeah, this also can be, but this one is, let's say, extreme case. This one not extreme case, by the way. This one not extreme. This actually is all the time we know about. It's VCC is all the time like 15 volt. So this means that my output is restricted between minus 15 to 15 volt. But yes, if I'm considering the temperature effect on the resistance, it can be nonlinear. Who can tell me another nonlinear phenomena, let's say? Now, let's consider the following system. Do you remember the tank, our tank? Let's assume this is the pump, and I need to fill up this tank. Now, the pump is pumping a flow, Q of the pump. Now, Qin is equal to 0 or equal to Q pump. Here I'm having a reservoir. Huh? Anyone? Saif? Saif.
معك دكتور.
Saif. Now, I'm pumping a water with certain flow rate. At some time, the Qn here will have value or 0.
مبدئيا أول إشي ما راح تكون في value لأنه كله راح ينزل هون.
Yes, so I must fill the reservoir. Then after that, I will start filling the tank, correct?
صحيح.
This called dead zone, which means that I'm having input, but there's no output. So if I need to plot it, if this is the input, and this is the output,
راح تضلها صفر أول إشي. يعني العلاقة راح تضلها ملزقة بالصفر أول إشي ثابتة لحد ما يتعبى الديد زون، بعديها راح تصير تطلع.
We have a bad signal, huh? So let me do it in my side. I will switch my network to yeah, good. So simply, this means that I'm having input, but there's no output. And this is what we call a dead zone. This is also another type of nonlinearity in the system. Huh? Yep. Okay. So here we stated that we need to study a linear time invariant system. For linear, I think we understand that any system fulfill the superposition principle is a linear system. Any system violate the superposition principle is nonlinear system. So we restrict ourselves to what? To a linear system. What about time invariant? What about time invariant? What about time invariant? This means that the characteristic of the system does not depend on time. Yes? So simply this means that here the characteristic of the system do not depend on time. Which means that if I'm having a system and I'm injecting the input at certain time u of t, I will get y of t. If I inject u of t after certain time, I will get y of t after certain time. Yes? This is what we call it a linear time invariant system. Yeah? Who can give me example for linear time varying system? Any system that the characteristic depend on time. Simply I'm having the time. Yeah. So in this course, we will study the linear time invariant system. For short, it's linear time invariant system. And the linear time invariant system is described by an ordinary differential equation. Or what we call it ODE. And you know that the ordinary differential equation is linear if the coefficient of the differential equation is constant. So for example, let's assume the following circuit. Okay. This is RL circuit, correct? Yeah. This one is RL circuit. Yes or no? Okay. So I need to model it. I need what? To model it. So if I need to model, the first thing you should specify what? The input and the output, correct? Because the model actually is a relation between the input and the output, yes? So let's assume that the input is the voltage and the output is the current. Yeah? So here I'm assuming that the input is the voltage and the output is what? Is the current. And I need to model this system. So if I need to model it, how I can model it? Huh? How I can model this circuit? Yes.
دكتور ناخذ KVL.
KVL. So simply, actually, in this course and even in all control, we have either electrical system or mechanical system. For the electrical system, I'm having three components. The first one is the resistance, and I know the relation between the voltage and the current is V is equal RI, and I'm having here inductance L, and I know that VL is equal L di by dt, and here I'm having a capacitance C, which I know that VC is equal 1 over C, the integration of I dt, correct? And for the mechanical system, all the time we are using Newton's second law, which is the summation of the force is equal the mass multiplied by the acceleration. This is whatever the system, we can solve it using only those, let's say, formula. Now, this actual circuit consists of resistance and inductance in series, so I will use KVL. If parallel, I will use KCL. KVL states that what? The voltage must be divided. The voltage around the loop is equal to 0. So V is equal VR plus VL. Then the input is the voltage. So this is the input equal. The output is the current. So this will be IR plus L di by dt. Now let's see. R and L constant or varying?
Constant.
Constant. So simply those are constant. So this is an example of what? Of first order ordinary differential equation. Yeah, correct? Yes. Another example. Let's assume that I'm having the third derivative by dt plus alpha 1 or alpha 2, let's say, the second derivative plus alpha 1, the first derivative, plus alpha 0 is equal to certain input u of t. This one, ordinary differential equation.
نو.
Why?
في مشتقة ثالثة وفي مشتقة ثانية.
No. The ordinary differential equation has no relation with the derivative. It has a relation with the coefficients. If those coefficients are constant, then this is ordinary differential equation. Why? Because here I'm having the third derivative alone. Here I'm having the second derivative alone. Here I'm having the first derivative alone. And here I'm having the zero derivative alone, which is the function itself. Okay, good. This will be the x. Huh? So this is ordinary differential equation. But what about if I'm having d squared x by dt multiplied by dx by dt multiply or plus 2x equal to u of t? This one
non-ordinary.
It's non-ordinary differential equation. Actually, this one is non-linear system. Why? Because here I'm having two derivatives multiplied by each other, correct? This is not or non-ordinary differential equation, which means that this is not a linear time invariant system. Yeah, good. So the differential equation is ordinary if the constant or if the coefficient of the differential equation are constant, correct? Yes. Now let's assume we have another example here. And for that, let's assume we have a circuit R, L, and C circuit here. And let's assume this is my output. I'm interested here, V out. And this is the Vn. And I need to find the mathematical model that represents the relation between the output and the input. This is the R, this is the L, and this is the C. And the same thing, this is a very simple problem. This is, I can solve it using the KVL series circuit. So here I will say that Vn is equal to VR plus VL plus VC, which is the V out. Yeah. Then now I will write Vn equal VR. In the first stage, I will write it Ri plus VL. I will write it as L di by dt. And VC is actually V out, so I will write here V out. Now we need to represent the relation between the input and the output. So the current passing through the capacitor is the same, correct? IC here. IC equal to I. So VC, which equal V out. What the relation between the voltage across the capacitor and the current passing through the capacitor? What the relation between the voltage across the capacitor and the current passing through the capacitor? This one, huh?
Integration.
This is VC equal. If I need to find IC, I will differentiate, correct? C dVC by dt, yeah? If I differentiate this one, I will get this one, yes or no? So simply here, yeah, simply here, the current I will equal C dVC by dt, or this will equal C dV out by dt, correct? Now I will substitute this one where in the current here and the current here. So what I will get, Vn is equal to RC dV out by dt plus LC d square V out by dt square, the second derivative, yeah, plus V out. Now, R, L, and C are constant or varying? Here I'm assuming it's constant, correct?
Constant.
So this is actually an ordinary differential equation, yes?
Oh.
This is actually an ordinary differential equation. Now, this ordinary differential equation, what's the order of it? The order is the highest derivative, and here I'm having what?
Second.
So this is a second ordinary differential equation, correct? Yeah. Good. Good. Now, until here we managed to find the model, yes? And we stated that we need the model in order to what? In order to capture the main feature of the system, or in order to analyze the system under specific excitation, under specific input. Which means that given the input, Vn, given Vn, I need to find what? V out, correct? I need to find V out. Yes? If I change Vn, I need to see what will happen to V out. If I reduce Vn, if I increase Vn, or what suitable Vn I need to impose to the system in order to achieve desired V out, correct? Which means that in the end of the day, I need to find a solution for this problem of the ordinary differential equation. Yes? I need to find what will happen to the output if I change the input, which means that I need to find a solution. Yes? And the solution in general for the ordinary differential equation is decomposed in two solutions. Yeah? The transient response and the steady state response, correct? Yes? So the solution of the ordinary differential equation is the solution of the ordinary differential equation is decomposed of, if this is my y of t, let's assume here I'm having dny by dt to the power n plus let's say k n dn minus 1 y by dtn minus 1 until I'm reaching plus k, let's say 2 dy by dt plus k1 equals certain excitation u of t. This solution y of t here has y steady state plus y transient. Or simply in the math, you call it what? The homogeneous solution plus the particular solution, or the natural solution plus the forced solution. So this is actually the steady state solution. And this is the transient solution. This is the complete solution, correct? Yeah? Yes?
Yes.
Okay. Now, question. Which is easy to solve differential equation or, let's say, algebraical equation? And for that, I will ask Yusuf. Yusuf al-Badr.
دكتور معك.
Which is easy to solve, differential equation or algebraical equation?
Algebraical equation.
Algebraical equation. It's more easy to use, huh?
Yeah,
So now, what about if we found a mechanism in order to convert the differential equation into algebraical equation? This will be very interesting, correct? Yes?
Yes, doctor.
And this is the function or the objective of what? Of Laplace transform. That's why in control system, we need to understand Laplace transform and the inverse Laplace transform. Why? Because I can convert the differential equation into algebraical equation by using Laplace transform. And for that, for short, let's assume that the Laplace transform for certain function, let's say f of t, is equal f of s. Yeah. And the Laplace transform for df by dt is equal to s f of s minus f of 0. Now to this stage. Now just a minute. This is the capital letter. This is a small letter. Do you know the meaning between them? This function in terms of Laplace this actually the time domain function. So, and this is the initial condition, what we call it, huh? This actually we call it what? The initial condition. So let's recall our RL circuit. It was Vn equal to Ri plus L di by dt. And let's take Laplace transform for RL circuit. So taking Laplace transform is simply state that I need to take Laplace transform for this one, and I need to take Laplace transform for this one. Yes? Now this is a function, so Laplace transform for it is what? Vn capital in term of s equal. R is constant. We know this one can be separated to be what? Laplace transform of Ri plus Laplace transform of L di by dt. And this also can be simplified such that the constant is out from the transformation. So Laplace transform of the I plus L Laplace transform of di by dt. So now R, Laplace transform of function is the function capital in term of s, plus Laplace transform for the index for the derivative is what? We already defined it here. Huh? Is what? Is L s I of s minus L because multiplication I of 0. And if I'm assuming that the initial condition is equal to 0, I of 0 is equal to 0. Now what I'm getting? I'm getting Vn of S is equal R plus L S, and I'll spread the variable, and this will be I of S, correct? Yes. Now I need to find what? I need to find I of t actually. Yeah? I need to find I of t. I need to find the solution for a given input. So this means that I need to find I of t given Vn input. So now, can anyone solve this equation with respect to Is? Tariq Samer.
نعم دكتور.
Can you solve this equation with respect to Is? Can you give me Is equals what?
هي Vn of S over R plus Ls.
You see how easy it is? Correct? So simply here I'm having a solution. Here I'm having what? A solution in terms of Laplace, which is very straightforward. Why? Because dealing in algebraical equation or solving algebraical equation is more easier than solving differential equation. So the relation now, who can give me the relation between the output and the input? I of S is the output, the input is Vn of S, and this will equal 1 over R plus Ls. Right? So this actually what? The output over the input equals certain function, correct? Yeah? This one, what we later will call the transfer function. So this one is the transfer function.
دكتور هو نفسه الجين اللي كنا بندرسه في سايكل 2.
It's the gain, but simply the gain is restricted to be at certain frequency. So if I need to find the gain at the DC gain, then the frequency is 0. Then S equal to 0, and this will be 1 over R. Yeah? Yes?
No, تمام.
Good. So this is actually, yeah, it can be the gain. Why? Because in the end of the day, if I call this one G of S, where is it? G of S, then the output I of S is equal certain gain G of S multiplied by what? By Vn of S. So simply this means that I'm shaping the input by certain transfer function to get what? The output. Yeah? And this one is called what? The transfer function. So now I can define the transfer function G of S as Laplace of the input over Laplace of the output at 0 initial condition. At 0 initial condition. Yep. So let's assume that we have the following example. X double dot plus 5 X dot plus 4X is equal to R, of course, it's T, T, and T, and T. I need to find the transfer function, and the transfer function is the Laplace transform of the input. So you know that this one is what? The second derivative. Huh? This one is what? Second derivative. So instead of writing d square x by dt square, I will write instead x double dot. Yeah. Now, what about if I'm having d4 of x by dt to the power 4? What I will write? If I'm writing x 1, 2, 3, 4, it will be time consuming. Huh? Instead of that, I will write it as x, and between bracket, I will put 4. So this indication of what? Of the fourth derivative. Yes? Good. So now, for this system, I need to find the transfer function. So the first thing, I need to find Laplace transform for this equation. I need to find Laplace transform for x double dot of t. And I need to find Laplace transform for the 5x dot. And I need to find Laplace transform for the 4x. And I need to find Laplace transform for the r of t, the input, under the assumption that I'm having 0 initial conditions. The first one here, who can help me with the Laplace transform for the second derivative?
دكتور أنا
يا تفضل.
هسه بدنا نحولها فبنحط اس تربيع.
The power of the derivative, correct? S2. Okay.
X of S.
X capital of S, which is the transfer function. Okay.
Plus X of S. S X of S.
Which is the second one, huh? First derivative, so this would be S. Then I'm having 5 X of S. Okay.
Plus
4
X of S.
X of S equal to
R of S.
R of S. Why? Because we assume that the Laplace of any function g of t is equal to what? G of S, which means that I don't know this one. If I know it later on, I have this. I have what? Expression for that, correct? Now I need to find the transfer function. The transfer function is what? The ratio between the output over the input. Yeah, the ratio of the output, and the output here is what? X of S, and the input is what? Is R of S. So this will be 1 over
S تربيع زائد 5S plus 4.
Yeah, simply here I'm separating the variable, correct? X squared plus 5S plus 4, all multiplied by X of S. This equal R of S, correct? Yeah, and this actually is what? This actually is what? Is
transfer function.
Yeah.
Transfer function.
Yeah, this actually is the transfer function. Good. So g of s, huh? So g of s here is equal 1 over s squared plus 5s plus 4. Now, what about given x of s over r of s equal to 2s plus 1 over s squared plus 3s plus 2? Who can give me the differential equation that represents the system? Who can give me the differential equation that represents the system? Which means that I need to find what now? I need to find the system in time domain, correct?
دكتور حيكون عندنا اس تربيع اكس اس زائد 3.
So the first thing I must separate, I will say that this will be s squared x of s plus 3s x of s plus 2 x of s is equal to s r of s plus r of s. So it's very simple to deal with algebraic equation. Then now I will use something called Laplace inverse. So Laplace inverse of x of s is what? Is x of t. Yeah.
صحيح.
Laplace inverse of s to the power n x of s is what?
هي المشتقة الام.
X to the power n, huh? Which is x or dn by dt to the power n, correct? Which is the nth derivative, huh? The nth derivative. Good. So now who can give it to me in time domain? The first one here, this is second derivative, third derivative, or the first derivative?
دكتور الاكس هاي second derivative.
So this will be x double dot plus 3 x dot plus 2 x equal to r dot multiply by the 2, correct? Yes.
Right.
Plus r. So this is actually what? This is actually an ordinary differential equation represented in time domain. Yeah. So until here, what I need you to understand, given ordinary differential equation, I must find the Laplace transform for that, correct? I need to find g of s, the transfer function. Yeah, and given the transfer function, I need to find what? The ordinary differential equation. Yes? Yeah, it's very simple until here. Good. Another example. What about if I'm having x, the third derivative, or let's assume that I will use instead of that. Yeah, plus 10x, the second derivative, or let's assume I will use the same thing here, 2, plus 15, the first derivative, plus, let's say 3x equal to the integration of r of t plus x of t dt. So this is an example of what? Differential integral equation, correct? Yes? Yeah? The first question, the order of the differential equation is what? What's order? This differential equation has what order?
3.
One more time. Come.
3.
3. Who agree with the
أربعة.
أتوقع 4. Why?
لأنه لازم نشتق عشان نخلص.
Yeah, because I need to get right from the integration. I need to differentiate. Yes. So if I differentiate all the parts, I will get x to the power 4 plus 10, x to the power 3 plus 15, x squared plus 3 to the first derivative minus x of t is equal r of t, correct? So now the order is what? Is fourth order. Now who can give me the transfer function, which is the ratio between the output x of s over the input r of s, equal to what?
راح يكون 1 على اس تربيع اس قوة 4 زائد 10 ضرب اس قوة 3 زائد 15 اكس قوة تربيع زائد 3 اس ناقص 1.
Yeah, correct. So it's very simple. It's very simple. Now, what I need you to understand, in this course, Laplace is a tool, which means that it's not signal system here to discuss with you how the origin of Laplace and so on. No, for me, Laplace is what? Is a tool. I need let's say understand how to go from time domain to S domain, from time to the S domain. And I need to understand how to return back from the S domain to the time domain. Why it's very important to do that? Why it's very important to return back to the time domain? Because in the end of the day, I need here to find the solution x of t. This is my solution in time domain. Yeah. Simply here, if I need to find the solution in the S domain, then x of s will equal g of s, the transfer function, multiplied by r of s. So if I specify the input, I can find what? The output. Yeah. But in the end of the day, this is a time domain problem. So I need to find the Laplace inverse of what? Of x of s. So next time I will discuss with you the basic, let's say, functions in Laplace, and how I can do the Laplace inverse in very simple and straightforward direction. ويعطيكم العافية. في أي سؤال؟
يعطيك العافية دكتور.
يا السلام عليكم.
أنا شفت الدكتور محمود بس أول مرة تستخدم مايكروسوفت.
دي خلنا أسكر. اوكي.